Good morning. My name is Marjorie Ray, and I'm going to have a talk concerning the crystallization of water vapor, or what may we discern from a snowflake. Let me give you a disclaimer here. We're going to actually be talking about snow crystals. It's aggregation of snow crystals or what make up snowflakes. But in this talk, I tend to use snowflake and snow crystal interchangeably. When Ralph was so kind to ask me to come here, he had recently seen a film by a young Russian filmmaker that he found very intriguing. And fortunately, I was able to make the acquaintance of Mr. Ivanov, and as a very wonderful and gracious person that he has allowed us, though this is a copyrighted film, for us to use his film for demonstration purposes. So it's about a 2-minute long film. It has beautiful music, and I hope that you enjoy it. So what we just witnessed was the crystallization of water out of the vapor phase of water. Now, if any of you have ice cubes in your glasses, then that's crystallization of water out of the liquid phase. But we actually, so that sort of miraculously appeared out of thin air. Of course, we're talking about water. Water is the most studied molecule in all of science. Something that we take for granted is really somewhat miraculous. It is made up of the most common element in the universe and the most common element on our planet. Each, the hydrogen and the oxygen, have 3 naturally occurring isotopes, which are going to be important for later discussion. Water is knowing what we know about hydrogen and knowing what we know about oxygen, we would still probably not be able to predict water. So it is truly an incredible molecule, and still under tremendous study. This is, maybe this recognized from your high school chemistry. These are Lewis dot diagrams which explain how atoms interact by sharing electrons. And the thing that makes water so amazing is that by sharing the electrons, it gives so much stability to the hydrogen and the oxygen by completing the number in their most outer electronic shell. So the A, B, and C are depictions of what is actually happening when the hydrogen and the oxygen come together. In the C panel, you will see that the shared electrons are now replaced with dashed lines, which are saying that those are covalent bonds. Those are some of the strongest bonds in chemistry. And that's just sort of a pictorial representation. Water actually looks more geometrically like the structure that you see on the bottom. And that's because you have two shared set of electrons, two pairs that are not shared. And they tend to be closer to the atom, to the oxygen atom, and they push the hydrogen. So here's even a better representation of it. And this is what gives the water molecule one of its most amazing, and what contributes to its wonderfulness, is that there's actually a charge difference, a polarity of this molecule. One side of it, the green that you see in this, is positive, and the backside, where the oxygen are not in contact with the hydrogen, is negative. And though the molecule is polar, pure water is not. In fact, pure water cannot conduct a current at all. And when you're trying to, for experiment purpose, make pure water, you actually look at the conductivity, and as your conductivity drops, that's a representative of how pure the water is that you're getting. Trust me, it is not an easy proposition to make pure water. But of course, we're talking about crystals, so we're now going from either a liquid phase or a vapor phase into the solid phase of water. And it can crystallize into many forms, but by far the most prevalent one is what is referred to as hexagonal ice. And this is a picture out of an old friend of a textbook. It's Leninger. It's the biochemistry text that I learned from. And it shows the red balls here are representative of the oxygen. The little small white ones are your hydrogens. The covalent bonds are by the solid little columns, and then the little hash marks are actually where the molecules are interacting with each other. The hydrogen from one molecule of water is being attracted, which is negative, is being attracted to, opposites attracts to the positive side of the positive and negative sides of them are interacting. So this structure that you see is something that we use in all forms of crystallography, be it an inorganic or an organic molecule, is called the crystal lattice. Water has what, and particularly hexagonal ice, has a thing that's referred to as, it's sort of a statistical thermodynamic term called entropy, and it's very low. And that means that it is very easy to predict where these molecules would be within the lattice. So let's move on here and look at this hexagonal ice, but let's put it into motion for you there. And so you can see a little bit better how the hydrogen on one molecule interacts with the oxygen on another molecule. And this is what gives water its stickiness and its fluidity, but also how when it's freezing, it stays in place, it locks into place. The hexagonal structure is a really a structure we see much in nature, and if we get into this discussion phase later on, we can talk about something that perhaps Phil will, the honeycomb conjecture and the mathematical proof for it, which is just an amazing discussion. But the hexagon is truly an incredible structure to talk about in biology. But the thing about this hexagonal ice is that this is the start of every snow crystal. Every snow crystal starts out as a three-dimensional hexagonal prism with the 2 basal facets and 6 prism facets. Now, this three-dimensional hexagonal prism can be flat like you see in some, chunkier, long columns, but they're always a hexagonal crystal. That is what is the nucleation point, the very center of a snow crystal. So let's look at some snow crystals. These are actually naturally occurring snow crystals, and these pictures were taken by an amazing man who, because of Ralph's asking me to do this, I have got in contact. Kenneth Lebrecht is considered the world authority really on snowflakes currently. He is the chairman of physics at Caltech. And he was very gracious when I approached him about using some of his copyrighted material, that he granted me to use whatever he had. And for that I'm very grateful. So a lot of the information in this talk comes from Ken's research. And so for that I'm very, very grateful. But these are actually naturally occurring snowflakes that he captured out of a snowstorm and took pictures of, and of course he uses different filters. But if you will look closely in the center of these, you will see the hexagon. These are very, very clear. You actually see the hexagon. And the one that's up in the most right-hand corner, let's take a little bit, maybe bigger, closer look, and you might be able to see kind of the hexagon in the hexagon. Now, this obviously is a very, very complex structure. And we're going to talk about 3 of the processes that have been described that lends itself to this or participates in this complexity. There's faceting, branching, and edge sharpening. So we're going to talk about these into some detail. But these 3 processes, along with many others, and the actual molecular shape of the water, give rise to the physical morphogenesis that we see. In the previous slide you saw that they certainly do not look alike. They have different, they are different morphs of course, water. And so this physical morphogenesis is the spontaneous creation of pattern and form by an inanimate material, the process by which order arises from chaos. So we think about just water vapor hanging around, but then it comes into the lattice and it gives order, okay? So this is an ordered, the whole thing is sort of an ordered process when you're talking about morphogenesis. But let's first talk about faceting, which is, of course, the beginning of each snow crystal. The little balls each represent a water molecule here. And what happens is that as a water molecule comes in and approaches the ones that have already moved into the lattice, on the smooth surfaces, they can come in because there's no real bonding potential there. They'll come in and then they'll bounce off. But in the areas where you see where it's irregular, there's more bonding potential there. They'll come in and they'll stick. And so, but this tends to go from somewhat disordered to more ordered. And so this is the nice little edges, that you see, particularly in the beginning, okay? And so this is a type of sort of ordered growth. But then you have to get that complex structure that we saw, we have to start seeing branching, okay? And branching occurs, this is a great, one of Ken's really good cartoons, it literally happens because those corners stick out further than the sides do, and so the molecules begin to gather up on those corners. And so then it encourages more branching and more branching and more branching. This is a type of growth instability. Okay, it is not as ordered as the other. So, as you saw, and we'll look at some others in more detail, that it may grow faster here or it may grow slower there. I'm going to show you some another really amazing movie. But one of the things that affects whether something branches a lot or it doesn't is how slow the crystal grows. If you slow it down, it causes it to branch more. And these are some very good examples. Now, these are not out of nature. They didn't come out of a snow cloud. They came out of Ken Lebrecht's lab. And he makes designer snowflakes, so we're going to look at some of those. That's what he calls them. And so, but this slide is really interesting because these are grown on like a glass slide in a microscope, so he can actually film them. And so you'll see this one that is on the left. You see the area around it where it's called a zone of clearing. And then you see the water, which is precipitated out of the vapor phase into the liquid phase. So you're seeing droplets of water on the edge. And if you'll notice that on the very edge of it here, those are smaller, they're lighter and everything. That's because they're giving up their water molecules to the vapor phase, and the vapor phase is what is feeding the crystal. And it has to, as it takes on more and more water, they have to travel further, right? They have to travel from here to here than when it was really close. It didn't have to go. And so this encourages more and more branching, okay? And so, of course, the one on the other side is just about finished, while this one is just starting. And, of course, you can really see the hexagonal crystal from the beginning in that one. So this is called diffusion limited growth. And it's one of the things that, of course, encourages all this beautiful branching. Now, what I'm going to show you here is one of Ken's movies that he gave us permission to use. These are what are called designer snowflakes that he makes in his lab. This is speeded up. It lasts about 30 seconds. It's a 2-minute, it's a 5 to 6 minute process, and it's compressed time lapse so that you can see it. But you already know about branching, and you know about faceting, and you know about diffusion limited growth, and you're going to see all this. It's fast, but see if you can't catch it. Pretty neat, huh? Yeah, right. It's really it's really quite amazing. Another process that is going on here is a thing called edge sharpening, which is also a form of instability, and Ken explains it really quite well. So I'm going to read you a quote from one of his books. Actually, it is the book that is sitting on the table. I have show and tell today. It's on the table there for you, and please enjoy one of Ken's books. It's through the sale of his books. There's no public funds put toward the research that he does. He funds all of this research by selling of his books and movies and things like that. So, and it's a beautiful book, and so please avail yourself of having a look at it. But anyway, this is a quote from Ken. Turns out the growth of a faceted surface depends on the width of the facet. When the last molecular terrace is less than 100 molecules wide, roughly, it becomes especially easy for molecules to attach to the top of the terrace. Strange, but that seems to be part of how ice works, something they still have no explanation for. This quality tends to sharpen the crystal edges when a corner grows. It produces narrow, faceted terraces. A narrow terrace grows faster than a wide terrace, and the growth then adds more terraces that are even narrower than before. The result is this edge-sharpening growth instability. So this is an unstable type of growth. So it's this, as you saw in the movie, this constant ordered, disordered, and all working in sort of in a unique harmony at one time to produce your snow crystal. Okay, so we're talking about what produces all these different shapes. So we're talking about morphology. So this slide is actually a presentation of a number of morphologies that we see in snow crystals. So you have plates on top of pedestals. You have hollow columns. You have needles. You have the flat plates. You have an example of one that's branched up there. So these are all morphologies of crystals that can be observed, both in nature and in the lab. And that brings us to this, what is called a morphology diagram. It's it's referred to as the Mackaya diagram. This diagram was produced, this data was produced by a really famous Japanese physicist named Yukichiro Nakaya. It was produced in the 1930s in his lab in Japan, both by observations by natural snowfall and him making crystals in his lab. So let's look at this diagram a little bit more closely. This diagram is still very much a mystery. We don't have explanations for everything that is being depicted on this diagram, so we're just talking about physical observations. So your y-axis here is the supersaturation of water. So this point down here where it says 0, 0, that's 100% humidity. Okay, so it's greater than 100% humidity, or the water vapor is what is referred to as supersaturated. Your x-axis here is, of course, temperature, either on a centigrade or a Fahrenheit scale. And then the curve that you see drawn in is the actual curve of the water saturation that they observed. They took this observational data in their laboratory situation and also took a certain amount of it as they could out into nature. And so by doing this and looking at the observations, you'll see that in less than the first, going from 0 to -5 degrees, you get plates, okay? And then when you get up to about 4 or 5 degrees and go out to about 10 degrees, you begin to see things that are more like columns. And then you move over, after about 10 degrees, you move over to where you see plates again. And then you move out and you see a mixture where it gets really cold, lower than -22 or so. You start seeing a mixture of columns and plates. Now, just think about this. This is pretty amazing. Look, let's just take, for example, the hollow columns. You're seeing hollow columns. They may have the same amount of humidity present, but look at the vast differences in the temperature. -8 degrees as versus almost -28, -30 degrees, but yet you're getting the same morphology. Okay? Why? And there's still not a really necessarily good explanation for that. So this is still an amazing diagram, very used. I think it's reproduced in that book. Ken talks about it a lot, and he uses it in almost every publication book that he does. Now, we've all heard that no two snow crystals or snowflakes are alike, and so we're going to offer one. This is just one explanation of how they are very different, okay, and this is somewhat on the atomic or isotope level. We talked earlier about there being isotopes of both the hydrogen and the oxygen. Hydrogen, we're going to talk about really the first two. The first one is regular hydrogen, which is referred to as protium, and it means that there is one electron and one proton in the nucleus with one electron going around. But hydrogen 2, which weighs, if you'll notice on the weight, is almost twice as heavy as hydrogen 1, and that's referred to as deuterium. That's what you hear about heavy water. So the difference is that there is a neutron sitting in that nucleus. Okay, so the weights of these one is almost twice the weight of the other. Okay, now how prevalent is it? Okay. 99.985% of the hydrogen on our planet is protium, but 0.015% is deuterium. Okay, we're really not going to talk about tritium, though. Tritium is really important for a lot of biological testing, but we're not going to get into that one. But then oxygen also has 3. The most 2 is the regular oxygen, oxygen 16. But the second most prevalent one is oxygen 18. 17 is really strikingly rare. So your 16 is over here again, 99% of the oxygen present on our planet. but about 0.2% of it is oxygen 18. So when we look, knowing that we have 2 hydrogens and 1 oxygen for every water molecule, we can see that in looking at prevalence, or abundances, if for every million molecules of, quote, regular water, that's just 2 protiums and an oxygen 16, there's about 311 molecules where one of the hydrogens is deuterium. And then for about every 2,000 or so, the oxygen, instead of it being 16, is now 18. Okay, so you can see the possible combinations just in looking at those. And so Ken offers a very wonderful explanation of this, and I hate to read to you, but it's such a good description, and this is in that book. Now, a snow crystal might contain a billion, that's 10 to the 18 molecules of water, give or take a few. And we see on average 1 in 500 of these will be different from the norm. Furthermore, these rogue atoms will be randomly scattered throughout the crystal with many, many, many different possible configurations. Really, it is a mind-boggling number of possible configurations, more than all the protons and electrons in a million trillion universes like our own. Thus, the probability that 2 snow crystals would have exactly the same layout of these molecules is utterly, vanishingly small. It could snow day and night until the sun dies before 2 snow crystals would be exactly, precisely alike. That's just one explanation. Okay, there are others. And so those, that only really describes the molecular complexity. There are other complexities that are going on too. What about the physical or meteorological dynamics that determine the final snowflake, the wind, temperature, humidity within a snow cloud containing an undeterminable number of microenvironments? This is why the morphology diagram is still somewhat of a mystery. A general morphological description can be made for the type of crystal that will form, but the final pattern is beyond the ability of science to predict. Similar, yes. Identical, no. Another process or property of snowflake is a process called molecular self-assembly. This is kind of a hot topic in science. Molecular self-assembly is defined as a process by which molecules adopt a defined arrangement without guidance or management from an outside source. In other words, we don't have DNA telling it what to do. And Ken offers a lovely quote here, so I'm just taking his words. The snowflake is a very simple example of self-assembly. There is no blueprint or genetic code that guides the growth of a snowflake, yet marvelously complex structures appear quite literally out of thin air. And actually self-assembly and the attraction of the water molecules into the lattice is one of the factors that drive physical morphogenesis. Emergence is another kind of hot topic too, particularly in some people that are on a little bit more of a philosophical bent, but and emergence is defined as a process whereby larger entities, patterns, and regularities arise through interactions among smaller or simpler entities that themselves do not exhibit such properties. This is saying that a water molecule doesn't look like a snow crystal, and a snow crystal doesn't look like a water molecule. Okay, so what makes it up doesn't, but it's the interactions, of course, that we've been talking about. Okay, so in the above review about snowflakes and snow crystals formation, everything that I've said has been really described in a purely mathematical, natural, we use physics and chemistry and mathematical terms to describe what was going on here. No supernatural explanations were ever put forward in anything we've said so far. Okay. But the data reported that about flow snakes is definitely, it's not deterministic. They're all different, right? But is that totally true? It depends on the scale of the observation. On the macroscopic or gross level, giving water vapor supersaturated and the correct meteorological conditions, snowflakes are produced. Snow can even be predicted to occur with some accuracy. So with future scientific discovery, more refinement of predictive model, will man's accuracy of snow prediction reach the deterministic threshold of no randomness? Perhaps, or most probably, one only has to look at the history of man's accuracy of predicting physical phenomena like eclipses and tides to see how science takes on the task of describing physical processes in the material world. On the molecular and micro level, each snowflake appears to be unique and perhaps challenges naturalism. But once again, much of the uniqueness is explicable in purely physical terms, in other words, discoverable terms. At the current time, individual snowflake morphology is not predictable, but the processes, faceting, branching, edge sharpening, are becoming more explicable, more understandable. This is the industry of science. This is the arena of the scientist. Dr. Lebrecq eloquently states his place in this particular scientific endeavor. Quote, "The snowflake's six-fold symmetry was explained in the earliest 20th century. When X-ray crystallography revealed the hexagonal structure of the ice lattice, and then crystal faceting was worked out in detail in the 1950s. Dendritic branching was solved for non-faceted branching in the 1980s. And the faceted branching seen in snowflakes was first demonstrated on the computer in 2005. The edge sharpening instability was only discovered a few years ago and is still well understood. The morphology diagram is still an unsolved scientific puzzle." End quote. So I'm going to play that again so that you can watch it grow, and I'm going to keep talking here. So what quality or qualities of snowflakes, snow crystals, could challenge the mechanistic naturalism that is somewhat pervasive but not limited to science? Mechanistic naturalism is really a philosophical term attempting to assign meaning to scientific inquiry. So we tend to want to put meaning, and so I made this because I particularly used the word parsing. We want scientists to fall somewhere on this continuum. And the word parsing says to analyze something as speech or behavior, to discover its implications or uncover a deeper meaning. So this slide, this is one way you could look at this continuum. You could just as easily flip it and make it, make it that way, whatever you like. But let's look at some terms that we've been using. Mechanistic is defined as of or relating to theories that explain phenomena in purely physical or deterministic terms, determined by physical processes alone. In physics and mathematics, deterministic allows for no randomness. This is to say that the same starting condition will always produce the same result, and snowflakes obviously do not fit in that. The Oxford English Dictionary defines naturalism as an idea or belief that only natural as opposed to supernatural or spiritual laws and forces operate in the world. In practice, some scientists embrace a more specific form of naturalism referred to as methodologic naturalism, which has been defined as the assumption that observable events in nature are explained only by natural causes without assuming either the existence or non-existence of the supernatural, and so considers supernatural explanations for such events to be outside of science. It holds that the scientific method, this is hypothesis, prediction, testing, and then retesting and repeat again, is the only effective way to investigate reality, physical reality, and that such empirical methods will only ascertain natural facts, whether supernatural facts exist or not. In other words, science can prove nothing. Prove nothing. Mechanistic naturalism denies the supernatural, while methodological naturalism claims nullo contendere. We do not contend on that front. Popular and public explanations for intelligent design and creationism are examples on how to reconcile the material world with the spiritual world. But is a reconciliation even needed? Is a belief in the supernatural and the practice of science in opposition? Perhaps looking at the extremes may define a reconciliation need. On one hand, there is the extreme scientist, materialistic, naturalistic, atheistic, who holds the supernatural believer to be a self-deluded, factual denialist. On the other hand is the extreme believer, fundamental, either biblical, Islamic, out of some tradition, unquestioning follower who holds the scientist to be a God-denying ideologue with delusions of naturalistic causation. Right? We got two huge things. Okay. There are certainly notables in each of these extremes. We've probably all been there, read some of them, okay? Diametrically opposed extreme views are seldom, if ever, reconcilable for many reasons. Inflexibility, hubris, ego, investment, whatever. Fortunately, on the whole, the majority of humanity functions somewhere in between. So methodologic naturalism and having a belief in the supernatural are not mutually exclusive. And perhaps that is where the 51% of scientists place themselves who believe in God or supernatural power when questioned in 2009 by the Pew Research Council. This is a really interesting diagram, but 51%, and studies like this have been done in years before. But when you take the scientists and break them down a little bit further, this is even more interesting. Okay, now this was in 2009. Now, you know how valid this study is. This was by the Pew Research Council, which is it's a worthy organization. At the time that they did the questioning was in 2008. They were questioning the people that were members of the American Association for the Advancement of Science, AAAS. At that time, there was over 138,000 members, and 2,533 of them self-selected on an internet questionnaire. So these people have self-selected themselves. But here's something that's really interesting to note, is that if you're by age particularly, younger people are considerably different than older people. Now, the cautionary tale here is that this group here is where our brain trust in science lie currently. That is the National Academy of Science. That's where the group of supposedly the cream of the crop of scientists in our country reside. And the statistics on them, though they don't like to give very many statistics about themselves, they were actually questioned in the late 1990s. And Now this group was not like in the previous study across the board with biological life sciences. This group is only represented by mathematicians, physicists, and astronomers because they were comparing it to some earlier data. And so in 1996, when they began this project, there was only 517 people that were part of the academy at that time who were either mathematicians, physicists, or astronomers. Only 50% of them, slightly more than 50%, responded. And so this data only represents about 260 members at that time. And so the disturbing part is that really only about 7% of those espoused any sort of personal, personal belief. Now, let me move on. There are notable exceptions to this, and I'm going to talk about those people in just a few minutes. But the Urantia book actually gives a beautiful explanation of a methodologic naturalist. Science should do for man materially what religion does for him spiritually, extend the horizon of life and enlarge his personality. True science can have no lasting quarrel with true religion. The scientific method is merely an intellectual yardstick wherewith to measure material adventures and physical achievements. But being material and wholly intellectual, it is utterly useless in the evaluation of spiritual realities and religious experience. Let me catch up with myself here on my... The belief or non-belief by a scientist is a rather peculiar question. Do we question the beliefs of our plumbers or our stockbrokers or our mechanics? Or why scientists in particular? Because a scientist's belief system has little or nothing to do with the acceptance, either by the general public or his colleagues, of the usefulness of their scientific data. Until they step outside of the realm of science and enter the realm of philosophy. The Urantia book kind of quote gives us a little bit of direction on this too. The universe is not like the laws, mechanisms, and the uniformities which the scientist discovers and which he comes to regard as science, but rather like the curious, thinking, choosing, creative, combining, and discriminating scientist who thus observes universe phenomena and classifies the mathematical facts inherent in the mechanistic phases of the material side of creation. Scientists are not philosophers. So when they make philosophical statements, they're just making them just like anyone else. However, there are notable exceptions to these. John Polkinghorne, Dennis Alexander, Arthur Peacock, Charles Towne. Charles Towne was such a gift to America, and if you have never, a Nobel laureate in physics and a Templeton Prize winner. His 4 comparisons between science and religion should be mandatory reading. It's just, he's amazing. We lost him in 2015 at the age of almost 100. But I would Charles Towne. So I highly encourage you to do that. Let's move on. Another quote, quantity may be identified as a fact, thus becoming a scientific uniformity. Quality, being a matter of mind interpretation, represents an estimate of values and must therefore remain an experience of the individual. When both science and religion become less dogmatic and more tolerant of criticism, philosophy will then begin to achieve unity in the intelligent comprehension of the universe. there's a lot of people now on this trying to, the conversation between science and philosophy and theology is, in my appearance, in my belief, is just seriously on the brink. I'm going to participate in the summer session at the Faraday Institute for Science and Religion this summer. It's an international course, and it's going to draw some amazing scientists and theologians and philosophers to it. Universities now have course tracks in science and religion. So the conversation is really moving, moving forward here. And there are a lot of people making a tremendous effort, and one of those that is making that effort is one of our own, Jeff Waddles. And in a blog, Jeff wrote in 2014, "Any fact that science truly discovers may be interpreted by philosophy as harmonious with any truth that religion proclaims. Philosophy can harmonize scientific truth, with spiritual truth because all truth is God's truth. When scientific discovery is mixed with an anti-religious philosophy, we can keep the discovery but abandon the associated philosophy. We can transplant the scientific discovery into our own garden." So I'm going to also give you a quote from probably the greatest scientist of my lifetime. "And though he did not believe in a personal God, on more than one occasion, Albert Einstein did make this statement, that science without religion is lame and religion without science is blind." So now we're going to look at our snowflake again, but I'm going to turn the sound off so I can continue to talk while you watch the beautiful movie. So returning to the snowflake, what can we discern? Science can be a passion that takes enormous commitment, as seen in Dr. Lebrecht's study of snowflakes, all of his pictures, movies, books, and papers. Science demands rigor to give accurate descriptions of the phenomenon under investigation: hexagonal ice, faceting, branching, edge sharpening, isotope lattice building. Science requires time, and the scientists of today stand on the shoulders of the scientists who have gone before. 400 years of snowflake studies. Science is accelerating. Snowflakes studied for over 400 years, but major scientific advances in the last 100 years. Science moves onward, pressing the boundaries of man's ignorance of the physical world. We went from gross observation to X-ray crystallography to computer modeling. So snowflakes offer a convincing argument to mechanistic naturalism? Maybe, maybe not. Well, more investigations bring more understanding of the conundrums that snowflakes pose to the existing body of knowledge of the material world. Most probably, yes. Will this knowledge prove anything about God, faith, or the spiritual world? No. Will snowflakes continue to inspire the scientist, the filmmaker, the artist, and the casual observer? Absolutely. Where that inspiration leads the individual is a personal decision. Thank you for your attention, and we can now discuss. Thank you. Yes, and I hope this is a discussion. So,
one observation I'd like to mention is that the question, do you believe in a personal God? And the question, do you believe in a God, are very different.
absolutely.
And we need to keep that in mind. Because when you introduce the concept of a personal God, you then bring into the picture all of one's past experience related to their religious upbringing and their exposure, throughout their life's experiences and all of that. And so that colors the question very dramatically. So when you read surveys, the results of surveys, it's extremely important that you ascertain exactly what the question was in reference to belief.
Absolutely. Please.
What comes to my mind with your presentation, I guess, in some ways we're all snowflakes.
Actually, it says that in the Urantia book.
It does, okay. Well, we truly are. I mean, we start kind of the same, and then we branch out, and we have different interactions, and we grow differently, and that's what comes to my mind.
Yeah, I've got that as a quote at the end of my paper, so take a look at it. But there's actually a quote that says exactly what you just stated. Anyone else?
I have a question on the symmetry of some of the snowflakes. I noticed some will get off a little bit off their symmetry.
Actually, more of them do than don't. It's just that Ken happens to pick the most beautiful and most symmetric looking ones.
Okay.
Yeah.
So that would make sense because some of these complex snowflakes are so perfect that you show.
Well, they are, but you need to look in the book. You'll look at them, and you'll look at one. So in fact, he gives you two pictures where they look almost identical when you at first blush. But then when you start looking at every edge and everything, you'll find out that they're actually really quite, one arm, though, when you look at the gross, it looks very similar to the other arms. You'll see that there are very amazing little differences in them. But he picks the most beautiful symmetric ones. Of course, he does thousands to get those.
So but the isotopes is what I was actually going to to, because if you have, let's say you're using the oxygen 18 atom, and if that causes some sort of, does that mean that 18 is on all of those things? That's why it all, so I'm...
No, that's what he's saying, is that where the randomness of that within the flake itself, it might be here and then it might be there. One leg may have some oxygen 18 and one other ones don't, it's such, tremendous randomness, and because the weights are very different, it's going to change, so let's say, for example, on this leg, you got, at this particular point of the branching, you've got an oxygen 18. Well, let's say it goes off at 20 degrees, where on this one it doesn't have oxygen, it only goes off at 19 degrees, okay? But that's going to make a huge difference, really, in the morphology of the flake.
That was an amazing paper.
So, well, thank you. I appreciate
Well, I
it.
agree. Thank you for doing that.
Well,
I was sorry, when you ask your question, could you speak louder so the audience that's watching can hear you? The microphone can pick up your voice, but when you're too low, they don't hear the question, and it's very important. Unless you repeat the question.
oh, okay. Okay, I'll be glad to. And also, you need to state your name. I'm sorry, Joanne told me to say that, and I fell down on my job. Forgive me. But you should say your name if you want to.
Okay, well, I'm Dave Newfer. Most of the natural snowflakes would start high in the atmosphere and take that time to do their formation.
Well, they begin to tumble through, and then as they tumble through, of course, more and more of the complexity is built in, because more and more water vapor is is recruited into the crystal, and so depending upon how it tumbles and does, you'll see snowflakes where there's one side of the crystal has no arms and the other has a lot of arms. So those are more of the rule, but as they tumble through, and then of course you actually, those are the crystals, and then when you get to the point where you actually make a flake, which is an aggregation of the crystals.
So how do they reproduce that in the laboratory?
Oh, well, and it's like we do protein crystallography. You can, and they do a technique that's called seeding. It's, in other words, you start with a tiny, tiny ice crystal or a seed crystal. In nature, we didn't talk about, even though I had it on there, is the nucleation event. In nature, what starts the snowflake off to begin with, if there's not ice crystals already in the cloud, a lot of times what they find is in the very center of the ice, of the crystal, is a dust particle. But recently, in the past few years, there's been, there's a really good paper, I've got it referenced in my paper, of where they looked at some snowfalls all over the United States, and they found out that like on 1% of all the snowflakes that fall, the center of it as DNA containing, in other words, organic containing. So this has a lot of implications for predicting particularly transport of plant pathogens and things. I mean, so this is how things are so interdigitated. But it's that nucleation event that starts. So in the snow cloud, it starts usually either with dust or an ice crystal. Well, they do the same thing in the lab. You have to start it off with something.
Is it like on a plate? Or
Yeah, it's on a slide, and they drop their, and they have it in a humidity chamber where they can regulate. They can produce that curve that was on the morphology diagram by putting a certain amount of humidity into the atmosphere in their growth chamber. And so they put the seed in there, they equilibrate their temperature, and then the humidity goes in, and then it begins, and the crystal begins to grow. And this is, we use it a lot in protein crystal growth. It's called vapor diffusion. There are many ways to grow a crystal. You can grow things called, for protein crystal growth, we do a thing called liquid-liquid diffusion, there's vapor diffusion, there's different ways to do it. But that's how they do it for ice crystals in his lab, is that they do the seed on the thing. And see, it's all under, it's in a cold room, and they have very fine temperature control, and he has a wonderful microscope, a beautiful microscope, and so that he can take pictures, and his microscope, of course, you saw the movies, so that's how he does it. But yeah, he will only make that crystal, though he'll use the exact same conditions again, he will only make that crystal one time.
Nigel Nunn, you put your two talks together. It's that unbounded complexity of what crystalline formation, the unimaginable complexity of these nanomachines, and what's that evoking is this idea of the mechanical non-teachable. So you've got the Precambrian explosion where the organised organelles start to do their thing and evolve, but leading up to that, those previous 2 billion years, where you've got snowflakes doing their thing, where you've got shells forming around bundles of other stuff. So that complexity, that's eye-opening. The possibilities for this idea of a mechanical, non-teachable domain of quasi-living stuff.
Good observation.
Garth Jameson, and the question, Marjorie, by the way, thank you. Fabulous, amazing, worshipful.
I appreciate it. It's Ken LeBrecq, that's the man you need to
Well, exactly. My nephew is in a group with Ken.
Oh, he's
And it's
wonderful.
a group of scientists, and they sit around and they talk about what might be possible. And it's this kind of discussion group that I think is the leading edge of what you're talking about. My question is the difference between emergence and molecular self-assembly. They seem very similar, but if you could articulate.
Yeah, they are, the self-assembly is a really hot topic right now, mainly in organic, because that's how they're growing, like these nanotubules and things like that is in self-assembly. It is different from emergence. They're really kind of two different sort of things. It's maybe you should ask me that offline. I got a really long discussion about it, but let's do it if you don't mind.
Okay. So emergence doesn't imply any kind of molecular self-assembly.
Not exactly. They can kind of one sort of it harkens to the other, but not necessarily. There's a lot of discussion about those.
Okay.
Anything else?
Phil Calabrese. Emergence always seems to be used when they don't have another explanation, but they want to make it a natural thing. So it emerged. I mean, it covers all possibilities. It emerged. So, I mean, self-assembly is a lot more specific. Emerge, to me, means somehow it emerged. It's like, here's where there's a big gap, and we don't know, so we're going to say emerged. It sounds natural.
My sense of it is that
That's sort of, yeah, I mean, it's when you get into the math, I mean, that's a great definition about how, much more simplistic than mine, but yeah, excellent. Yeah.
that self-emerging systems is kind of an umbrella term, whereas molecular self-assembly is perhaps a subset of that kind of understanding.
Yeah, it's kind of, I guess.
I've just heard emerge so many different contexts that I defy somebody to be able to define it and collect it, you know, actually get all of the applications in the definition. I think it's a very vague term used to sound mechanistic and natural when there's no explanation for how this came about.
Right, right. Another question. The Pew Research, I think feeding a little bit off of Ralph, in my opinion, there are category confusions here in the question and the methodology of the question itself. So when you ask the question, do you believe in God, but you don't believe in God, but you believe in a higher power. So somebody, for instance, like Einstein, he was asked to be the first prime minister of Israel. In my opinion, he declined because he did not subscribe to the theology of Old Testament images of God. But it's clear to me in reading his philosophical texts that he clearly had an idea of a supreme, in fact he calls it a supreme intelligence in the universe. And whether or not he attributes personality, I think again in the Urantia book, a way of understanding, is an appreciation of what personality is. And so much of our appreciation of personality is rather primitive and immature. So that the question, do you believe in God, or don't believe in God, but you believe in a higher power? Well, it's an awkward question, I think. Don't you? Do you agree?
Oh yeah, I totally agree. I mean, it's, you know, it's like any survey, it's not ideal. And are you actually testing the question, what you're trying to get at, you know? And so, absolutely, I agree with that. But I think they were trying to give a space for people to go to that did not believe in the idea of a personal, you know, God as it's defined by, I guess you would say, the Christianity or whatever tradition that you go out of. But yet there's, you know, a category of people that very much like Einstein, they don't see him as a personal thing, but they certainly see evidence of a higher power out in, you know, active. And, you know, there's a whole, I happen to have a very good friend who's a monk. He was a physicist first and then became a theologian. And his real area, his real interest is divine action in the world. And there's a whole group of folks that are constantly talking about that philosophically and theologically. And so I think it was to give people who didn't necessarily have some type of religious place, harbor, you know, where without saying, well, I'm, you know, an atheist, so to speak, you know.
Yeah.
So.
In my classroom, I often, when students come up and say, I'm an atheist, I always ask the question, tell me about the God you don't believe in, because I probably don't believe in that one either. And I believe that most people have a pretty childish, puerile concept of God, like the ancient Greeks living on a mountain, living in togas and drinking wine and having wonderful parties. I think some of the even modern Christian, Muslim, Jewish concepts of God perhaps are an evolutionary step forward, but not too far removed from some of those more anthropomorphic images. So I think part of the question in this whole discussion is, what is our definition of God? And is God a God, or is God God? That distinction between a being and being is huge. In fact, I would say it's infinite.
But to get back to our scientists and being a methodologic, in other words, you're defining science purely by method, then you don't have to discount God. You can, it is totally consistent to have a belief, a very strong belief,
Right.
and still be a practicing scientist at the same time. And I have a very good friend that's chairman of the chemistry department, and Morgan and I were recently talking at a science and theology meeting, and I asked him, I said, what do you think about, what are you? Because he's a very strong believer, and he's an excellent scientist. And I said, methodologic naturalist. And he said, that's the only place we have. That's what, because they discounted the intelligent design. I'm not talking about the intelligent design like we've been talking about intelligent evidence. I'm talking about this more populist sort of considered almost a pseudo-theoretical thing, which is just, in a lot of my colleagues' opinion, it's just a shade off of creationism. They just kind of took the Bible out of it, but they're still using sort of the same reasoning to define it. And that's, as a theologian said to me, he thought that intelligent design was very poor theology. Okay. And there are, Francis Collins has dismissed both intelligent design and first creationism. But so where does the believing scientists reside? And they reside because they hold method in science. It's not going, it's this thing about using the word proof, as my friend Morgan says. In science, proof is a four-letter word. Okay? We never prove anything. Method only allows you to approach it, but you will never arrive. And so that's go ahead.
Well, mathematics is a science, and we do.
Right. That's the only way. Well, but I agree with you on that. But that is the only. I've been in.
We have assumptions to start with,
Right.
which aren't proved. But then we deduce things that are proved. So it is relevant to our assumptions that we prove things. So if you didn't have any assumptions, you wouldn't have proved anything.
Right. So, I've actually been in talks and defenses, particularly with graduate students, and they evoke the proof word. And somebody will immediately say, are we talking about geometry?
Right.
Because, it's because when you say prove, you have solidified something. The questioning has stopped. And science is all about questions. If you can, that's one of the problems with intelligent design. If you continually say, well, it's God doing it, then, okay, so God's doing it, so I don't have to investigate it anymore, then science stops, okay? And so it's this, and so that's where method becomes so strong. I agree that you're the only person in this room that has a proof. Okay, as far where science is concerned, but this is the harbor for a believing scientist is more in methodologic naturalism, I think.
But I think Phil makes a good point, and that is, it all begins with assumptions. And what I know in the philosophical realm, philosophical atheists, the primary assumption is God does not exist. So if you launch your inquiry with that assumption, you're probably not going to get too far in your mode of investigation. And that's why I think the Urantia book lays it out pretty well in terms of what's the methodology of science, what's the methodology of religion, and suggests that faith is not belief, it's not creed, it's a methodology. And it implies a certain attitude or curiosity toward the subject matter that you're investigating. And so I think as we launch any of this, we have to ask, what are our primary assumptions and what's our definition of God? What's our definition of personality? What are the definitions we're assuming in the conversation? Because I think if you took that Pew survey and you asked what was your definition of God, you would get a variety of definitions that would span the spectrum.
Absolutely. That was the only data I had, sorry.
I wanted to also say that there's a kind of statistical proof where you allow that there's a possibility that you have made that the conclusion is false, but you've reduced the probability of that down to some manageable level. It could be 5% or 1% or 1 out of 1,000 or 1 out of 1,000,000. So there are statistical proofs, but they're not logical proofs. They're probability proofs. I wanted to also say something about what you were talking about with respect to, do you believe in God, a personal God versus, because personality, if we talk about personality or personal God, people think of a gray-haired man with a large beard. So yeah, you have to define what you mean by a person, and you have to divest the concept of all the material, as the Urantia book says. It has to be a mind, it has to be someone who can know and choose, and the other things that personal persons can do. You might get a different answer in that case.
Yes, I think so.
Well, I think another piece.
This is more to
Marta
Elvis.
Thank you, my roomie. But I think we also use science to change our assumptions. And no matter what we start with a series of assumptions, a whole belief system. And then by further study, curiosity, exploration, we then say our original assumptions no longer fit. So we have to look deeper. And I think it's an ongoing process of believing, having our beliefs changed, expanding our beliefs. And that's how it works with the minds.
Bruce Johnson, I'd like to build on that. In our culture, the hardest thing to say is, I don't know. We want to know what's the answer, just get to the end and tell me what the answer is so I can move on. And it takes active intention to say, I really don't know, and keep that window of curiosity open. It's a partial answer, and be comfortable with that. Because we're finding kind of a tendency for the answers, and life is about finding all these series of answers. So to exercise the self-discipline to once in a while say, yeah, that's a partial answer, or that helps me understand. I want to understand more. I think we need to kind of nurture that quality in ourselves, and that kind of attitude versus this attitude of just get to the end of the story and tell me the answer so I can move on.
So technical difficulties coming in from a lady named Lynn St. Pierre. Do you know this lady? It says there's background noise. I believe
Well,
this
it's
is
just
from the Big
picking
Bang.
up from that microphone, because if people are playing with their things on the table, the microphone will pick it up.
Oh boy. Oh.
So be careful what you do with your things, the noise that you do, and also the connections here is pretty good, so maybe some people are experiencing connection at their own end. But here, by what I get, is that the signal is pretty good, so.
There's a comment kind of on the science, more hard science nowadays. There's an excellent book called Ignorance, What Drives Science. Has anybody read it, by Stuart Farson? He's a head of biology at Columbia. And he runs a class called Ignorance. He asks his students, they need to think about what kind of grade do they want. Do they want to get an A for ignorance, or do they want to get an But here's the premise of the class. And I actually have had a colleague who participated as a scientist in this class. He invites rather renowned scientists to his class. And it's not to talk about what they know, It's to talk about what they would like to know. In other words, they describe their ignorance. And where in most things, ignorance precedes knowledge, in science, ignorance follows knowledge, okay? Because what we do is we've pushed the boundary out and we've now come up against something, we've explained this, and now we've come up against the next thing that we don't know. And this is the scientific enterprise. It's an excellent, very readable book. You can read it in one sitting. He gives some really good talks on YouTube too. A really, really wonderful book. My friend, my colleague that participated in it said it was a really amazing experience, because most people, you know, when you give talks and things, you want to talk about things that you know. And it's really great to get in there and say, these are all the things I don't want to know. You know, this is what I find exciting. You know, these are the questions that I would like to have answered. You know, this is the real creative part about science. You know, how can we figure this out? You know, what's the next? And then this is the scientific enterprise.
And I think the history of science is fascinating, because the beginning of the 19th century, I think we all know, scientists were all proclaiming, we're done.
And now we're just saying, we haven't even scratched the surface. Let's go ahead now.
Nigel, no? In this sense, the true scientific method is really a technique for evolving our beliefs.
Mm-hmm. Absolutely.
Yes.
And
say your
our
name.
assumptions.
Say your name.
Say your name because some people
Phil
that
Calabrese again. And our assumptions, because we are always adding or subtracting or changing our assumptions, and then we'll find we can prove different things. So it's a double change axioms, change conclusions.
Ralph wanted to say
Ralph
something.
there. I'd like to just add that in defense of the scientific method, we do include our assumptions in our hypothesis. And when we propose a hypothesis, we are actually stating what our real assumptions are in terms of what we want to prove or disprove in a given scientific examination or approach. So that, from that point of view, I think the scientific method is a solid, reliable method of approaching any real question.
Any questions of quantity?
Material questions.
Yeah, but then you mentioned
That
quality.
quote about quantity and quality, the difference in quantity and quality.
Dynamic,
yeah.
it's interesting that there's a quality about things as well as a quantity factor. Concrete thinking and yeah.
Well, let me just, being a totally committed methodologic person, is that the science method is not going to prove or disprove. It's either going to be supportive or disproving of. It will never really be, you can gain support for your hypothesis. Then you go back and refine it and make it even more supportive, hopefully. That's how it works. It's here again, it's semantics, because if you get to the proof phase, it's done. Okay, the questions stop, then the science stops. So it's a mindset, and this is what, when you have students in your lab and everything, you try to get them out of this idea that they are going to prove something. That's an end point. Science doesn't end. Okay, you support it, your idea, and then you keep going. So semantically, you try to train young scientists to not, because it's just a solidification of thought when you start saying proof, that's a semantic thing, but for a true method scientist, it's a huge deal.
Nigel, none again. It's also worth mentioning that each generation of young students, the main game is to break the old model, rather than just fit in with reprove assumptions. But if you can break a model, well, you get all those prizes. That's the big
Is it ever? And yeah, that's the That's the ring, that's the golden ring there, right there. So,
I think Stephen Jay Gould has a nice image. He says it's the two magisteriums.
absolutely, yeah, it's
And
really.
I think if we understand that those magisteriums are connected, but they're not the same magisterium, then we have an approach to reality that's helpful. If we assume, as many of the scientists like Dawkins and Hutchins and these people assume, is that religion somehow should be a subset of physics, then I think you started out of the port with the wrong boat.
Well, you know, I mean, Dawkins has been soundly criticized for his very poor philosophy. He's not a philosopher, okay? He's a biochemist, you know, he's a biologist, and so.
But again, it's taking those.
It's when you step outside of science and make philosophical inferences onto, you know, everything else that you get in trouble.
You're using those scientific assumptions to prove or disprove religious realities. Good luck.
Yeah, it just doesn't, it doesn't work. It doesn't work. So, anybody, go ahead.
Yeah, well, you reminded me of how I would love to see a fellow on television, I've forgotten his name now all of a sudden, the scientist who had a long series.
Carl Sagan?
Sagan, thank you. And he would be so good at explaining things. And then he would drive me up the wall when he would say, now purely by chance. And I would always think, how do you know it's purely by chance?
It emerged.
It emerged there, Bill.
Bruce Johnson again. But I don't, I empathize with atheists. The information out there, there's bad religion out there. There's muddy water in a sense that I don't blame someone. I started out an atheist for many, many years. And I think it's an entirely logical step as you try to soak up what's going on in the world. So a lot of the problem is bad information on the religion side. That is really an obstacle, is one of the big obstacles. Carl Sagan's buried right down the road from me, by the way.
You're married a believer.
There's more to him.
That's called karma.
He wrote that book called Contact. It became a movie.
Yeah.
And it kind of opens this experience at the end. And I think steps like that kind of pave the way towards something larger. But I mean, that's an inspiring movie, I think, Contact. So we'll give Carl some credit for moving ahead, moving things ahead.
David?
Well, one of the first papers, the first paper has a listing or a summary of the names of God, and one of them that's most used in the book is first, source, and center. And it's totally approvable that that's, on some planets, that's what God is considered. How do scientists think of the first source? Is that something that you don't say it's God, you say is there a first source? Is there an origin to everything that there is?
I mean, Aristotle was probably the first to speak of a prime mover. He didn't really speak of God in personalistic terms, but he said there's got to be some uncaused cause to all of this. It only makes sense. But I think, what we learn in the Urantia book is unless we add the dimension of personality, then we have no capacity for relationship with that uncaused cause. It's merely an object of thought, which doesn't create, forgive me for using the term, but transformative self-emergence.
But the concept the concept of God is important personally to each of us, and really to scientists who don't believe in God as well. I mean, they wouldn't even be there.
Right.
But if you can consider the first source as God. Yeah, is that usable? I mean, do they use that? I mean, the scientists who don't believe in God, do they consider a first source, or do they just say like it emerged that people developed, that life happened on Earth? What parts of science is God an integral part, that, like biology, where life starts? I think that is one. Where cosmology is, where did it all begin? I'm just throwing that out there.
Yeah, thanks, Dan.
Wouldn't it be the particular scientists rather than the field? The sense would be, it's like, are you an orphan or do you recognize your parenthood? And is that something you look at? Is that something that you address? I mean, you could be as good a scientist, I would think, either way. But that it would be an enriching experience to be able to have the background knowing your parenthood as opposed to not knowing it. But I don't think any particular field. Perhaps when you get to some of the more softer sciences, there might be some more room for it because it gets into philosophy maybe more. But I think in general, the scientific method and the hard sciences, it would just vary scientist to scientist.
So Marjorie, I have a question for you. What's the difference between proof and certainty?
Ooh, that's a hard one. That's a really hard one.
You want to read your quote?
Yeah, well, I want to read a quote that Richard Keeler, bless his soul, loves to quote, and he loves to quote a lot of things. But this is paper 102. It says, of God, the most inescapable of all presences, the most real of all facts, the most living of all truths, the most loving of all friends, and the most divine of all values, we have the right to be the most certain of all universe experiences. Which is interesting. So there's a difference between proof and certainty.
Well, for me as a scientist, I don't really use proof per se, except in terms of mathematics, and that's sort of that's really a hard thing. I mean, that's a write it on paper type type thing. Where certainty is something that I have to come to within my own soul, my own heart, my own mind. So it's totally two different. One is a purely intellectual endeavor. The other one is a soul experience. So we're about to reach the end of our time.
I think Ralph had a...
Yes, Ralph, I'd just like to mention, certainty is a mind phenomenon. It's an opinion or a sense. It's a mental position that we've taken, that I believe this to be certain. Proof, on the other hand, is a much more fundamental, as you said, intellectual, and even perhaps materialistic position or phenomenon.
Mine is a little bit of a variation on what Ralph just said, just on what I've been doing with the brain piece. I would say that proof is in our belief systems. It's a thinking, processing piece. I would say certainty comes from a faith experience. And that my sense in terms of what I've been doing is faith is very different than the belief system or the knowing that the mind-brain combination can experience. And that it comes from a different place in us, whether it's the soul or whether it's an experience that transcends our brain mechanism in terms of a relationship with God. But it has, I think, a totally different feel to it.
One more time, Bruce.
Bruce.
Yeah.
Marge, I'm curious, this is a great education about snowflakes, but I'm curious about you and some of the values and interests of yours that kind of brought you up to being such a good resource for this. Just any background on you that led you to this kind of unique area of study?
Well, I mean, I'm a scientist. I was educated as a biochemist, protein chemist, and I did a lot of work in both lipid research and in protein science research, particularly protein crystallography. I was fortunate enough to have the Urantia book enter my life in 1975, and then acquire within a short period of time an amazing mentor in Jim Mills, and who Jim was, by the way, a chemist before he became a philosopher. You know, it's just how life unfolds, and you know, things that happen to us along the way. You know, it was Dick and I were having this conversation this morning, is that when you look back, now at 66, I can say this, when I look back, I absolutely see the plan, you know, but of course when you're in the midst of it, you don't see it. But now I can really appreciate some of the things and the opportunities. If I guess, I don't really have a regret, but if I said I had a regret, it was that when I was so blind to the multitude of experience, not that I'm not still maybe somewhat blind, but the multitude of experiences that are literally whizzing by us every moment. I was somewhat blinded to those in my early life, you know, because of focus on career or whatever. But all of it, you know, it's just. I mean, I'm sure everybody at this table could share the same, you know, type of experience. I've had a great scientific career. I've totally enjoyed it, doing stuff on the space shuttle and on the space station, and you know, working in different labs over the world, and you know, I've had a great scientific career. But now it's time to do something else. So now we're doing philosophy. So,
if I may add, we are the benefactors.
Well, thank you. But
and it's delightful to have you here.
Well, thank you. I have totally enjoyed it, and Ralph gave me such a great topic. I mean, I cursed him a few times, I have to say, and talked to him because I was like, I can't do this, Ralph. And he was like, sure you can. So he's been a wonderful, wonderful help. So thank y'all for inviting me. I really appreciate it being here with you.
On behalf of all of us, thank you.
Okay. Thank you very much.